sick. All right, so we've talked a lot about the rock cycle, right? We've gone through all three types, and understanding geologic time today is going to rely on what we've learned so far about the about the rock cycle, excuse me. All right, so fossils and things like that are actually going to be really important today. And we're going to be talking about how we find fossils, how we date rocks with fossils in them, all right? So, and we care because fossils can tell us a whole lot about what the Earth looked like millions of years ago. It's going to be very important for us to understand that. All right, so the first type of dating we're going to talk about is relative dating. And this is a way to figure out the order in which we find things like faults and folds, all the things that we've been learning about this semester. And most of the geologic timescale is reconstructed this way. So here is a picture of the geologic timescale. Up in the yellow parts in the left-hand upper corner, that's stuff most recent to today. And we move back and back and back through time to the beginning, 4.56 billion years ago, into the Hadean, which we've talked about in class. All right. So obviously, there's not cute little signs in the rock record saying, oh, here I am, I'm part of the Hernandian in the Ordovician, right? We don't have that. That's not what's going on here. But what we see are slight changes through time all over the globe that allows us to place boundaries so we can talk about the changing geology on Earth. So relative dating is a comparison. Like, Elise is older than her sister. I have no idea how old Elise is, and I have no idea how old her sister is, but I know Elise is older. So if we take a look back here, I know the Jurassic in blue, in the top of that second from the left corner, the Jurassic is older than today. That doesn't tell me any information about what ages there actually are, but that's a lot of information. Now that's in comparison to something like absolute dating. Fernando is 22. I know Fernando is 22. I don't know how old Fernando's siblings are, but I know Fernando is 22. So you might be thinking, okay, well, relative dating sounds kind of like a wash. Why would we use it? Well, it's actually incredibly important because really it's not super easy to figure out how old a rock actually is. And we didn't develop absolute age dating techniques until long after we already had relative dating. You don't need to write this down. It's just something to keep in the back of your mind as to why we use it. So we're going to be using stratigraphic principles today to figure out the layer or how things actually happen. So here's just a cute cartoon. We're going to be figuring out how we understand the geologic timescale today. So stratigraphy just means that rocks form in layers, and stratigraphy means we're studying those layers. All right. So these layers can tell us a lot about where they come from. Did they come from a beach, or did they come from a river? Did they form near each other, far away from each other, how old they are? Is this made out of sandstone? Is it made out of limestone? Who knows? It can tell us a whole bunch of information. All right. And again, I don't ask that you know any of the scientists we talk about in class, so don't feel that you need to memorize Nicholas Steno's name. But Steno developed 3 of the principles of stratigraphy in the 1600s, and we'll talk about those. So the first you're already familiar with, we just haven't put a name to it yet, but superposition means the oldest bits of the rocks are on the bottom. So the stuff that was laid down first is on the bottom. It gets progressively younger on top. Just like we talked about with anticlines and synclines, means the same thing. Then we have original horizontality. All right, so what this means is when sediment from rocks is being laid down, like all those bits of sand, before it's compacted, it's laying down horizontally. If they are pushed up in weird angles and things like that, that happened after the rock was formed. So here we have on the left side the rocks that are originally horizontal, meaning they're laying flat. And then on the right, something has happened. And you can see here, this is the beginning of a syncline, right? Where the limbs are dipping down. And finally, this last one, lateral continuity. Lateral means side to side. Continuity means unbroken. All right. And what this means is if we look at the left and the right here, this is how it formed on the left originally. All right. So just lots of rock, nothing wrong with it, all deposited horizontally. And then we had a river that came in and cut through. And you can see that it cut through, but that cutting happened afterwards. That is the principle of lateral continuity. All right. So those 3 things kind of dictate how we look at the rocks. Now, we're going to add a couple more onto this. And the principle of cross-cutting relationships was added by James Hutton, a Scottish geologist. All right. And we'll talk about the other stuff he came up with in a little bit. But cross-cutting relationship means a geologic feature that cuts through another is the younger of the two. So take a look at D. We're over here on the kind of the right side here, D. D cuts across A and C. D is younger than A and C. A is older than C because A is on the bottom, C is on top of A. But D cuts across them both, so D is the youngest of those. Does that make sense? Okay. So last one, I promise, is the principle of inclusion. So this is Charles Lyell. Charles Lyell was a very famous scientist. He was a big proponent of Charles Darwin and the theory of evolution when it was first described in the 1800s, but he also was a geologist of his own right. So inclusions is the clasts within a rock, so the pieces within a rock are older than the rock itself. So on the left, we have an example of a conglomerate. I know you were thinking it. All right, where we have those large rounded clasts within a rock. And on the right, we have a mosquito in amber that we could not ever pull the DNA from to recreate dinosaurs. It's just not how it works. All right. But an easier way to think about this could be the chocolate chip cookie principle. So the chocolate chips were put into the cookie dough batter. The chocolate chips were already formed long before the cookies were baked. So if this is the principle of inclusions, the chocolate chips inside the cookies are older than the cookie itself, right? We go to the store, we buy all the stuff to make the cookies, including the chocolate chips. Chocolate chips go into the batter fully formed, and they're baked into the cookie itself. Does that make sense? Sometimes thinking about it in terms of baked goods is way more fun than geology. All right, so now we're going to go through a couple more other things called faunal succession. Fauna means animal, succession means changes. So faunal succession just means we can track changes in geologic time based on changes in the fossils. So this image here isn't something you need to memorize, but take a look at the fossils you see here. These are trilobites, and they're related to fossils today, closely related to insects and other things. And you can see that they're changing. Well, that may not mean anything to you, but to me, I take a look at that and say, oh, okay, well, based on this change, I think this probably showed up at about this time in the geologic timescale. Again, here is our geologic timescale, and here is an example of faunal succession. This is pretty important because you see those same trilobites down near the bottom of this graph, near the Cambrian, and then we see things like dinosaurs in the Mesozoic, and you see that those two don't cross each other. So if I find a trilobite, I know where I am. If I find a T-Rex skull, I know where I am. If I find a mammoth elephant skull, I know where I am there too. So all of these together can help us figure out, figure out the relative ages that things formed. Okay, so lithostratigraphy. Lith means rock, stratigraphy means understanding the layers. So this is just lithostratigraphy is just a fancy word for using these rock layers to figure out ages. All right. And we're going to use all of Steno's laws and principles to get stuff together. So to do this, we're going to look at cross sections of rock, and they kind of look like a piece of cake. All right, so on the left, I have a cross section that I made. On the right, I have a piece of cake. They look similar. All right, and here is a very happy geologist in front of a cross section. So superposition, which one is the oldest? If you were thinking number 7 or the red layer, you would be correct because it is Y on the bottom, I assume you said. All right, there you go. Put in the answer there. Original horizontality. Rocks aren't likely to be deposited at angles. So which one is the oldest? So take a look at this. Which one is the oldest? Now, there's two options here. You could be thinking the one in the very bottom right-hand corner and the top left-hand corner. But if we're going to go with the simplest solution, which we should, it's going to be the one in the bottom right-hand corner, the green one. All right, so I didn't put an arrow there, but that little dark green one at the bottom right-hand corner. Okay, cross-cutting relationships. So when did the fault form? The black line, just like you saw in last week's lectures, first or last? It formed last. Exactly, it cut through all of the layers. All right, now these numbers don't correlate with the stages that they were formed in. These are just random numbers, but you can see that we had 7, 2, 9, 6, 5, 10, and then 3 because the fault cuts through all the layers. Okay? So now this is just a refresher. You already know this, but we have our hanging wall and our foot wall. And you can draw a little person to figure it out. The head will fall into the hanging wall. The feet will fall into the foot wall. All right, so what type of fault is this? If you're thinking it is a normal fault because the hanging wall has moved down, you would be correct. All right. So there you go. I gave you guys the answer here. All right. You can see that the hanging wall moved down to the current position. All right. There is just a normal fall, hanging wall moves down, reverse, hanging wall moves up. All right. So now let's bring us to unconformity. Now, conformity means conform. And to conform means everything should be about the same. So an unconformity means something's weird, something's missing. And what's missing is time. If you can imagine with me, every single piece of sand that's ever been laid down in Earth's history has not made it into the rock record. Weird things happen. Hurricanes happen. Tsunamis happen. We just have times where sand isn't laid down. All kinds of things can change how rocks are not being deposited, or maybe rocks are eroded and worn away. All right? So how we represent that in a geologic time is by a squiggly line. If you take a look here, we see that 7s, or the red lines, or the red areas, and we have 10, 9, 6, 2, 5. We see that 10 isn't represented on both, so we just represent a squiggly line. We know something's missing, so we put a squiggly line there. How much time? Well, I don't know. Neither do you. I can't tell, right? We don't have any of that information. So we just say that there's missing time. So an example of how this might affect our interpretations is, let's imagine that this is not a pile of rock, but instead maybe Harry Potter. And let's say we're in the first book of Harry Potter and we find out, oh, look, okay, Harry's a wizard. And the next thing we see is Harry's graduating from Hogwarts. We know we've missed something, right? We've missed a whole lot. And that's an unconformity. If we just ripped out those parts of the books, that would be an unconformity. All right, so here is the famous unconformity that James Hutton described. Take a look here at that arrow. You see how the rocks change directions completely? That's the unconformity. There's quite a few million years in there. So if you ever go to this place, it's Sicker's Point in Scotland. Take photos and send them to me. All right, this brings us to Walther's Law of Facies. And this sounds more complicated than it really is. But the idea is when environments are preserved in the rock record, they stack vertically, just like all the cross sections you've been seeing. Those are changes through time. The bottom happened first, the top happened last. And it means we can read the rock record like a book, like Harry Potter. Now, what if we have an unconformity? Can we read that rock record just like a book without any issue? The answer is no. So Walther's Law of Facies means if there is nothing that happened to that rock layer, we should be able to read it like a book. If there are any unconformities, well, that would violate Walther's Law of Facies. All right. So there's a question I just asked at the bottom. So yes, unconformities would violate it because there would be missing time. We can't read it directly. All right. So we already know this extrusive, we already know what that means, right? Formed outside the magma chamber, so it should be fine-grained, right? Volcanic rocks can also form in these layers. And here we have an example of a sill, right? So stuff being injected. Oh, sorry, that's a dike. It's happening at an angle. All right, intrusive rocks can actually follow cracks, voids, and they can force themselves in. And they can do this to sedimentary rocks too. And this is important for very good reasons. We can use this for absolute dating, otherwise known as radiometric dating, and we'll talk about that later. All right, so let's take a look at this. Number one, that triangular piece here with the axes all over it, that represents an igneous rock. All right, so here we have an igneous rock. So what is the order in which this happened? Okay, well, 7 is on the bottom, then we have 11, 9, 6, 5, 10, and then 1. Why is 1 last? The principle of cross-cutting relationships. 1 cuts across all of those. All right, and we can a lot of the times igneous rocks will be represented like with the little axes on it. The rest are sedimentary rocks. So that's just a symbol that we would use to represent it. So let's try an example here. All right, so we see here in the bottom right-hand corner, the brown layer there, that is the first layer. All right, and I put a little arrow there to help you figure that out. And then we're going to move to, we move to the purple, yellow, green, light brown, black, magenta, and light blue, right? So we're just following that pattern all the way across the screen to the point, where we get to that light blue. Now, what's the next layer? Well, you should say the unconformity. You can see the unconformity cuts everything off. Okay, so now let's move to the next layer. we see that I've highlighted these shells in there, and that's due to the principle of inclusions. The shells are older than whatever the rock layer is. Then the next layer is the green, the yellow, then that bed there, all right? So this is due to cross-cutting relationships, that's why I put that there. Then the orange, then the blue. All right, so that's an example. So now let's talk about biostratigraphy. If lithostratigraphy uses rocks to figure out ages, bio should use what? Life. And how we use life is fossils. So here is an example of fossils in the rock record. These are crinoid fossils, so the things that I study. All right, and we can use index fossils. So this graph is just showing you a general age map of different types of fossils that we could find. All right, but here we have index fossils here. An index fossil is something we can use to say, oh yes, I know exactly where I am in geologic time. An example of a good one is Lysostraurus. They show up in different times, like right around Pangea. But not all fossils make good index fossils. So let's talk about some useful traits. 1, excuse me, it has to be abundant. So here's an example of pollen grains. And it should be abundant because we need multiple data points to show where we are. Should be easily identifiable, meaning we need something that just screams, hello, yes, I am this fossil to a paleontologist. We need something that's geographically widespread. I need to be able to say, okay, this time in Russia, and this time in China, and this time in the US, and this time in Honduras are all the exact same. All right, so if this fossil only exists in one tiny piece of Kansas, well, that's not going to be very helpful to me. And I need something that's independent of environment, meaning it can be preserved in multiple different types of rocks. So I don't want to use something that's super picky about where it lives. I want to find something like a pigeon, right? A pigeon fossil. Pigeons live everywhere, right? So I want to find something that is everywhere. And finally, I don't want them to live too long, so they need to have a narrow range of time that they live in. I don't want something that lived for 100 million years. I want something that lived for a couple thousand years, because when I find it, I know exactly where I am in the geologic record. Here's just a picture of some conodont fossils. They all lived for a couple thousand years each, and then they died out. They're excellent index fossils. All right, so even if rocks look a little different, like in this graph here, you see that the two different layers where these teeth are found, they look a little different. But if I have those teeth, I can figure out what's going on. I can say, okay, well, even though these rocks maybe don't look exactly the same, I can still tell they're about the same age based on the fossils. All right, so here is an example, 13 events. All right. So I'm letting you piece together what's going on here. I'm going to stay quiet for a couple seconds. All right, so you're starting down at the bottom. You can see that we have a big red blob A that's cutting across a bunch of other stuff, so you know A can't be first. So take a look at E down there in the bottom. E is on the bottom. Then we have G. Then we have L, C, and then you can see that something's cutting across everything up till C. So what's next? H. All right, then we have M, D, J, that yellow brick looking layer, and then we have A. If you see, A is cut off right at J. So then next is N, K, B, and F. All right, now I'm going to give you this one in class, and we'll look at that one. So make sure you go back to this one and make sure you understand how this works. Okay? And there you go. We'll give you this one in class to work on. It's a lot of fun. All right, so arriving at absolute dates, meaning something happened 20 years ago, 65.6 million years ago. Human history is a very minuscule percentage of the entirety of Earth. So written histories only go back so far. So here is an example of a volcanic explosion. We know when this happened. This is Krakatoa. All right. So here is another example, right? We have an absolute date of one of these, and this is, we've talked about this example in class. Edward Munch might have painted this based on the Krakatoa explosion that he saw. It's not necessarily the most credible link, but it's a possible idea. So there's other ways that we can arrive at absolute dates. So we've talked a little bit about how North and South poles swap. So based on that idea, we can actually use the magnets and rocks to come at absolute dates. This is called magnetostratigraphy, meaning using magnets to find out the layers. All right. So the sun also switches, and we know that based on a 22-year cycle. I'm not going to ask that you know a whole lot about this because we've already talked about it, but just as a fun reminder. But we can make these maps that look like this of normal and reverse polarity. All right. And when these poles swap, we can make this map, and then we can pick out where the rocks that we're finding fall on this map and say, okay, yes, this rock was part of this normal polarity regime from 222 million years ago or something like that. All right. Now remember, the poles don't swap they don't swap on a schedule. We don't know exactly when they're going to swap. So it's not something that happens on every couple of years like the sun does. The Earth is not as stable with its magnetic field. We can also do things like dendrochronology. So trees. We can use trees to figure out how old certain things are. So some trees have lived a very long time. Some trees have died within the past couple thousand years, so we can use them to figure out how old certain things happened. We can find out droughts that happened a couple hundred years ago because we can see that in the lines of the trees, things like that. So here's the oldest tree, one of the oldest trees on Earth, about 5,000 years old. Dendrochronology is really great because it can be super precise. I can tell exactly when summer happened a couple hundred years ago, but it's only effective back to about 11,000 years. So since the Earth is 4.56 billion years ago, it's not going to get us super far. Now, how old's the Earth? I just told you, but I know you would have said 4.56 billion years ago. So how do we start figuring out how old the Earth is? So, Lord Kelvin, I don't need you to memorize this. All right, he determined the Earth was about 20 and 400 million years old via calculations. He did not understand radioactive decay, so the breakdown of materials on Earth. And radioactive decay adds heat to the system. Remember when we talked about the iron catastrophe and the remelting of stuff and the late heavy bombardment? We have meteorites smacking into Earth, melting stuff again. He didn't know this. So his calculation didn't know there was more heat being out of the system, which would have made the Earth older. All right. And here we bring to the best science joke that's ever been made. You ever hear about the guy who was frozen to absolute zero? He was okay. Haha. I'm done. All right. And here we have Becquerel. He actually discovered radioactive decay, and he shared the Nobel Prize with Marie and Pierre Curie about it in the 1903 Nobel Prize selection. All right. So we'll talk about him for a second. Isotopes. All right. So an isotope is the atom of a single element that varies in the number of neutrons. So we talked about atoms a little bit. We have protons, neutrons, and electrons. Protons and electrons, we don't worry about those with neutrons. Protons will always be the same, meaning carbon will have 6 protons no matter what. Hydrogen will have 1 proton. But we can actually vary the number of neutrons. All right. Some isotopes, when we have that varying number of neutrons, are naturally unstable. This doesn't make them bad. They're just unstable. And when they're unstable, they emit radiation when these unstable isotopes are breaking down. And we can measure that radiation. And this radiation is releasing heat into our system. Okay? Okay. All right. Not all of them are harmful. Everything around you is radioactively decaying. All right? So not everything around you is like a Spider-Man movie where like you touch something and then you gain superpowers. It's not how radioactive decay works. All right, and I know the rest of you are groaning because of my lack of knowledge about the Marvel Universe, but there you go. All right, so carbon 14, for example, is in all living organisms. The second you die, you start breaking down that radioactive decay. It's not harmful. Now, the original isotope before it breaks down is called the parent isotope. All right, so just like your parents came before you, this is called the parent isotope. After undergoing radioactive decay, what's left is the daughter isotope. And we can measure how old something is based on the amount of parent and daughter isotopes. All right? So, radioactive isotopes decay at a consistent rate. We know this rate. It's incredibly easy to calculate this rate. All right? So that means no matter the amount of parent isotope present in a sample, over time, about half of it will decay to its daughter. All right? Now that could be 5 years. It could be a billion years. It depends on what isotope we're starting with. Are we starting with carbon? Are we starting with oxygen, nitrogen? It really just depends. All right? So let's take a look at how this is going to work. A half-life means the amount of time that it will take for half of that parent to decay into a daughter. And again, different half-lives will have, or different isotopes will have different half-lives. So 1 half-life means we'll have 50% parent, 50% daughter, no matter what. After 2 half-lives, we'll have 25% parent, 75% daughter. 3, 12 and a half, 87.5. Hopefully you're seeing here that we're just having each one in 2. All right, so that's pretty easy to figure out. If I tell you I have 3.125% parent, you know that 5 half-lives have passed. All right, you don't necessarily need to memorize these numbers if you can divide things by 2. Now, let's give you an example. An isotope has a half-life of 2,700 years. 2,700 years. I find a sample with 25% of the parent isotope left. How old is the sample? Well, if there's 25% left, there's 75% daughter, so that means 2 half-lives have passed. So that would be 2,700 times 2, which is 5,400 years old. Does that make sense? Okay. So here are some geologically useful radioactive isotopes. You do not need to know this list under any circumstance. The only one I want you to kind of remember is carbon-14. So carbon-14 is usually touted as, oh, hey, carbon-14 doesn't, we can't carbon date things that are super old. It doesn't work. Of course, we know this. If you're taking a look at this, the half-life is 5,730 years old. Meaning, if we divide it by a bazillion, we're only going to get very tiny numbers that we can't measure. So we use other systems to measure the age of the Earth, like rubidium or uranium, that are much, much, much better at having a longer half-life. So here we have carbon-12 and 14. I don't need you to remember all of this. I just want you to understand why carbon, we don't use it, carbon-14, for radioactive or old measurements, all right? Carbon-14 is not stable. It breaks down into nitrogen-14. And this will happen to every living thing. When you die, you start decaying into nitrogen-14. So, half-life is pretty short, which means it's only useful for dating things that are pretty young. So here's an example of the McClung Museum. The McClung Museum has a large collection of Native American items in their museum, in the archaeology section. And along with indigenous scientists in the area, they date the objects found in these Native American grounds to figure out how old they are. All right, so this is just a painting of it. But carbon-14 breaks down over time. So we can't use the system for things that are older than 70,000 years. So if we want to look at something that's 500 million years old, we can't use carbon-14. So now let's combine the two. You've seen this chart before, but let's combine these two dates together. Let's say layer 2 is a volcanic ash bed that is 5 million years old. We know it. I just told you it is. You can't, yeah, that's what it is. The igneous intrusion that's cutting across it is 3 million years old. How old is the dark blue layer? All right. So the dark blue layer is between 2 and 6. How old is it? Well, can you give me an answer? You can tell me a range of answers. Oh, sorry. The answer is that it is between 3 and 5 million years old. So that is the most scientific answer you can give me. You can't tell me it is a specific number because I didn't give you enough information. So the answer to this question is it's between 3 and 5 million years old. Does that make sense? Okay. So using relative and absolute dates is how we have pieced together this beautiful geologic timescale. All right, that is how we have done it. So I'm going to show you a little bit about the terms that we use. I don't need you to write all this down. I just wanted to go through it with you very quickly. But these terms are based on the changes we see in the rock record. All right, so we have large units: super eon, eon, era, period, epoch, age, and chron. We're getting smaller as we go down. So the super eon is something called the Precambrian. It's everything that happened before fossils with hard parts in the Cambrian 542 million years ago. So we start with the Hadean eon. We talked about the Hadean in class. It's the beginning of Earth. It was named for Hades. And then there's the Archean, where we see the first evidence of life. The Proterozoic, where we see the first evidence of multicellular life. Exciting stuff. Here's an example of Dickinsonia, one of the first known large animals. Then we move into eons. Here we have the Phanerozoic that kicks off with a lot of fossils like trilobites. All right. So this is about 542 million years ago. The second is this is Phanerozoic was the eon. It starts with the Paleozoic era. All right. We're getting smaller and smaller and smaller. To the Mesozoic, which you're probably familiar with because that's where the dinosaurs are. to the Cenozoic, where we are now. It's called the Age of the Mammals. And then finally, we can get a little bit smaller into periods and crons. We're not going to worry about that here. I don't need you to know all of these different eras, eons, etc. I just wanted to show you how it works, okay? So here are the review questions. And make sure you watch this and understand it. We'll go through an example on Wednesday. All right.